Take her away. We don't want her.
I'm taking up to this. Okay, how about this? Does this make you guys feel better? Good. Now you have space.
You have to move down more.
Are you gonna shift her all the way to like the edge?
Look, I made space.
Move down more.
You need to push that way.
Move down more.
You had a question on your homework where we had to use molecular orbital theory to describe the bonding for the acetylide anion. It's on page 383. Practice example. So we're continuing the example I gave you yesterday. The bond, the order of the bond energies is based on what is contained on page 381. So you'll see on page 381, the bottom of the page, it says the energies are arranged according to sigma 2s, sigma star 2s, pi 2p, sigma 2p, pi star 2p, and pi star, and sigma star 2p for the acetylide ion. Well, they say for C2, and I'm assuming that for the acetylide ion it's going to have the same arrangement, and failing any other indication anywhere else in the textbook, that's what we're going to go with. So this is what I got. Page 383. B, that was your homework. Acetylide ion looks like this. Carbon normally has 4 valence electrons. So the 2 carbon atoms possess 2 times 4 equals 8 electrons to account for. An extra 2 electrons are added to account for the -2 charge. So the total is 10. Electrons. So we arrange the orbital energies according to what we see on page 381 of the text. So we have sigma 2s, and there's a box for that one. Sigma star, also from 2s, pi 2p, sigma 2p, pi star 2p, and sigma star 2p. One orbital, 2 for the pi, 1 for sigma again. So these are the orbital energies. And there are 10 electrons to account for. So you fill each orbital as you go from the bottom up. 2, 4, 6, 8. 10 electrons used up. Those ones remain empty. What is the bond order? Well, the bond order is equal to 1/2 the bonding minus non-bonding electrons. In this case, it's equal to 1/2. Number of bonding is 1, 2, 2, 4, 6, 8 are bonding, and 2 are non-bonding. The stars are non-bonding, and they're anti-bonding. So 1/2 of 6 gives you a bond order of 3. So the C-light ion is believed to have triple bond. C-light has a triple bond. And since it possesses no unpaired electron, it is predicted to be diamagnetic. I should say, this question comes from 10th edition of Brown and others. The name of the book is Chemistry, Essential Science. Molecular orbital theory was used to successfully describe the behavior of organic dyes. Organic dyes are substances that contain multiple double bonds that are conjugated, meaning that it's double bond, single bond, double bond, single bond. So when you have conjugated double bonds, it creates a space for electrons to flip back and forth. And the energies that correspond to those movements of electrons, to those resonances that electrons can occupy, are usually in the visible spectrum of light. So they involve wavelengths that our eyes can detect. So our eyes detect a very narrow band of electromagnetic radiation, which we call visible light: red, orange, yellow, green, blue, indigo, and violet. Combine all those colors together, you get what we call white light. At least that's what our eyes perceive. But there are many forms of electromagnetic radiation we don't perceive. So on page 385 of the text, they have an explanation of organic dyes. And they mention the concept of HOMO-LUMO, which is an acronym for highest occupied molecular orbital and the lowest unoccupied molecular orbital. So basically it's a recognition of that energy space that electrons can occupy, given by the presence of these conjugated single and double bonds. The energy difference between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, HOMO-LUMO, corresponds to the lowest excitation energy necessary to displace an electron in an energy transition. The more conjugation there is in a molecule, the smaller the transition. Therefore, in highly conjugated molecules, visible wavelengths of light are absorbed, whereas in non-conjugated molecules, the transitions usually occur in the ultraviolet range of the spectrum, which is invisible to the human eye. We don't see ultraviolet light. And they have a picture of beta carotene on page 386 of the text, where you can see the conjugation of the molecule. That was actually something I mentioned to you yesterday. I used to work at Humpty Dumpty, and I would add that precise molecule, beta carotene, to the caramel corn when I was preparing the recipe. So a lot of times when you buy food they'll add things to it to give it some nutrient value, because a lot of the stuff we buy is junk food. Even in cereal, they'll fortify with iron and minerals and B vitamins and so on, which is a good source of a lot of the essential nutrients. Okay, I think we should practice a bit more with the Vesper theory until you're comfortable with it. So I'm going to move us on to question 9:15 is a good one, the end of the chapter. It says, describe the characteristic electron domain geometry of each of the following numbers of electron domains about a central atom. So they have A, 3, B, 4, C, 5, and D, 6. It's actually a pretty long question. But we can make a molecule, sort of a hypothetical molecule with atom A and atom B. It doesn't have to be an actually existing molecule, but it'll help us focus on what these different domains do. Sir?
And B, where do you find that one, the anti-bonding?
Where do you find the antibonding? Well, you have to look up the literature on what it is for a particular molecule, but you see it on page 381 of the text, at the bottom of the page. The antibonding orbitals are the one that have a star next to the type of orbital that it is. So you have two types of bonds, sigma bonds and pi bonds. Sigma bonds happen when two orbitals overlap head to head, okay, like that. Whereas pi bonds happen when you have overlap of orbitals that are unhybridized and are pointing in different directions in space. So let's look at acetylene. In acetylene, you have orbitals that are formed by the hybridization of the carbon atom in an sp hybrid, and that's a sigma bond because the orbitals overlap head to head. But in that same carbon atom, there are orbital lobes that are extending above and below the plane of the atom. I have to erase this to show you. So let's say the px orbital, which is, let's suppose that one remained unhybridized. There's a px here and a px there, and they're pointing above and below, but they can actually interact side to side. So they end up looking like this. It makes a big fat lobe where they touch each other side to side. And that is a pi bond. In acetylene, which is C triple bond C, one of those bonds is the sigma. The other two are pi bonds. So this is one pi bond. It looks like two lobes, but it's actually one pi bond. There's another set of lobes sticking out like this, one behind, one in front. It gets really messy if I try to draw it. And they interact as well, and that's the second pi bond. It looks like a scribble, doesn't it? But that's what it looks like. I mean, I think later on in the chapter they actually show this. It might not be in this chapter. It might be in the next one. Let's see where it is. That's why I say I strongly recommend you read the whole chapter, because it shows this orbital hybridization. Yeah. You didn't see that? You want to see the rest of it? Then we can finish that. We'll continue with some examples from 9:15. I don't think it's only about an hour today because of the CLC. I'll just go fast as I can. Also remember we have, today's Wednesday, so Friday we have that periodic table test. You can watch the videos on it, because that's what's gonna be on it. I've made about 2 or 3 videos just on the periodic table, so you can watch those. And it's a repetition of the lecture I'm gonna give you on how to memorize all the different parts of the periodic table, and which parts I'm gonna ask you about. Fact. I started marking your periodic tables. I can see which students had me last year, so they're at an advantage because they're basically reviewing the stuff now. If it's the first time you have me as a teacher, you're gonna have to pick up a lot of material all at once. Well, I apologize for this rapidity with which you have to cover the material, but I don't apologize for the final result, which will be making you competent in chemistry. So, what are you gonna have to know for Friday? Since the others are copying right now, we can talk about that. You have to know the whole table. Alright, so you memorize it by making words of the groups up and down. So we all know that the groups are numbered 1 through 18. It goes 1, 2, all the way through 3 to 12 on the transition elements, and it goes 13 to 18. Each group has its name: alkaline metals, alkaline earth metals, transition metals, boron group, carbon group, nitrogen group. I think the nitrogen group also has its own name. The pycnogens or something like that. Okay, we're not going to use that. Nitrogen group. Chalcogens, halogens, noble gases. Then, of course, the metalloids are sitting on the step. So you see this thick blue line. Anything sitting on the step is a metalloid. Anything touching the bottom of the step with a full side is also a metalloid. So all these guys and these two. Aluminum and polonium are not really considered metalloids. In some textbooks you'll see they argue that polonium is a metalloid. Let's, for our sake, agree that aluminum and polonium are metals. And all the other ones are metalloids. Everything to the right is nonmetals. You notice that these red ones are all gases as well at room temperature. Also, the ones that are in blue are liquids at room temperature. These two are metals, gallium and mercury. The interesting thing about gallium is it'll melt in your hand like a chocolate, but it doesn't boil till around 2000 Celsius. So you can make some really good thermometers with gallium, high temperature thermometers. If you did the same, mercury boils at 400, so you can't really make, you can make some good thermometers with mercury too, but you can't go over 400 with them because they burst. Whereas a gallium thermometer will withstand up to 2000 degrees because it doesn't boil till 2478. Very interesting metal, gallium. It also has the effect of embrittling other metals. If you put gallium on aluminum, the aluminum becomes embrittled. It weakens it, and the metal becomes useless. The same thing kind of happens with mercury and gold. If you mix mercury and gold, it'll form an amalgam. The mercury actually filters into the gold and becomes part of the crystal, but it tends to weaken the metal. I don't know what the proportions are used. Dentists used to use dental amalgam where they had a mixture of silver, gold, and mercury, and that's what they would stuff in your tooth to plug your cavities. So if you look at older people, a lot of them still have those black fillings in their teeth. They're made of dental amalgam. Now, slowly they're going out of fashion because they're being correlated with mercury in the body, and that's not a good thing. No amount of mercury is good in the body. There's no safe dose of mercury. The less, the better. What else? You have blocks in the periodic table. These two are called S block because they represent filling of S orbitals. This is called P block because it represents the valence shell. The last shell of electrons is in a P orbital. So all these are P1, P2, P3, P4, P5, and noble gases are P6, which represents a particularly stable configuration. D block is all the transition metals, so they represent the filling of the d orbitals. Interestingly, in the d block, you'll see that a half-filled shell is stable. So there's some metals, like for example, chromium, even though it's in the 4th position in, so you would expect it to be D4, it's actually D5. So what's going on? What's happening is the S2 orbital is giving up one of its electrons and it's going to D5, and the chromium ends up being S1D5. So apparently there's some kind of stability involved in doing that, because also molybdenum does that. Instead of being D4, it's S1D5. And the same thing happens with the coinage metals. They should be D9. All of these should be D9, but they're all D10. And the S1 gets promoted, so that S2 shell, which should be filled, it ends up giving the electron up to the D shell. They become all of them D10. So the electron shell filling mnemonic is not always religiously followed. There's some deviations from the predicted configuration. And a lot of times there seems to be a special stability for when these things happen. As it turns out, these are coinage metals. They're all extremely resistant to corrosion, particularly gold. Silver reacts with sulfur, so it tarnishes, but it doesn't really corrode. So if you have silverware, it turns black over time, but you can easily repolish it because the sulfur in the air combines with the silver. And copper also likes to form coating. If you've ever seen copper roof or copper gutters on an expensive house, they start out looking copper colored and they slowly turn green, like the Statue of Liberty. Why? Because the copper likes to form hydroxides and carbonates. Forget which, maybe it's both. Anyway, it turns green. It forms a patina, and that patina it further protects the copper from any further reaction. So copper can be used as a roofing material. You can have something a millimeter thick, and it'll last hundreds of years before corroding, if at all. What else do we need to know about the periodic? We need to know, so the shell filling mnemonic, obviously, I think you all know this. Goes like this. Can I erase this now? Yeah. Shell filling mnemonic goes like this. These are all s orbitals. I know there's no 8s, but it preserves the triangular pattern and makes it easier to remember, so I do it. Where would you have an 8s orbital? Where would you need to invoke an 8s orbital if there was an element that had enough electrons to fill up to 8s? Where would it appear? Right there under francium. Francium is period 7. So this is 7s1, 7s2. So if there were an element that had 119 protons and not 119 electrons, it would have an 8s1 orbital. So this doesn't actually exist, but I put it in there because it just makes it easier to draw the pattern. P on the second here, then you skip these two and you write 3, 4, 5, 6, and they're all Ds. Then you skip 2 and you write 4, 5, and these are all Fs, and the filling order is like this. Lowest energy, highest energy. Bottom of one row goes to the top of the next one. And the electrons pile into the atoms that way. You should know the diatomic elements. You can use that off-Brinkel and AT, which is rarely listed but would be diatomic if you could find some on the earth. They don't bother listing, but I do. Off-Brinkel at. Those are diatomic elements. You might also add in that phosphorus is tetraatomic, sulfur is octaatomic. What else? The electronegativity series. Not the electronegativity series. Yeah, actually, electronegativity. We'll do that first. Electronegativity, which is a measure of the attraction that an atom has for its for electrons within a bond. So if you have a covalent bond, and there are two atoms forming a covalent bond, one of them is going to have a stronger attraction for the electrons within that bond than the other. So it has a higher electronegativity. Electronegativity tends to increase from left to right and from bottom to top. So the most electronegative element is fluorine. Remember, these are usually excluded in electronegativity measurements because they don't tend to form, they don't easily form bonds. There are very few compounds with noble gases, which is why they're called noble gases. They don't tend to form any connections with the riffraff of the other elements. So the electronegativity series just lists the important elements, the ones that you find in most organic compounds. So fluorine, oxygen, nitrogen, chlorine, bromine, carbon, hydrogen, and then the metals. Metals have very low electronegativity. They are typically the ones that are losing the electrons. And if you think about it, the non-metals are the sort of the schoolyard bullies when it comes to electrons. They're the ones grabbing the metals by the lapel and saying, give me your lunch money, or your electrons, either way. So fluorine is the biggest bully when it comes to taking electrons. Oxygen is also a very strong oxidizing agent. It likes to take away electrons. So when you see these molecules, when you see especially these two atoms within a molecule, you know that the electrons will likely be closer to them. The example par excellence is water. Water is composed of hydrogen and oxygen. Oxygen has a high electronegativity, so you'll see a slight negative charge closer to the oxygen and a slight positive charge closer to the hydrogen. And that's what causes water molecules to interact with each other. You get the dipoles interacting. So the oxygen from one atom, from one molecule interacts with the hydrogen from another molecule, and the same with the hydrogen from this molecule and the oxygen of that one, and that's what you get. You get a hydrogen bonding. It's a dipole-dipole interaction, of which the one in water is a particularly strong example, and creates hydrogen bonding, which is the explanation for many phenomena in nature, from things as simple as curling your hair, to the super winding of proteins, to why you can wet your finger to turn a page, because you're using hydrogen bonding. Without realizing it, you want to turn a page, you wet your finger, you get hydrogen bonds, and the finger sticks better to the surface. The other thing you should know by memory, because it comes in handy, is the activity series. It's a long list of atoms that if you put them in a situation where they're competing for the same position, the one that's higher up on the activity series will push the other one out. And the way you memorize that is you make a mnemonic. It goes lick, ba, ka, na, kana, magal, min, zinker. I'll explain in a second.
Or activity series.
Look, kind of magal, min, zinker, pico niacin, PBH, QAG, UgPatau. So you'll notice that the elements at the bottom of this list have a reputation for being not very reactive. Platinum, gold. Well, you know, platinum is so unreactive, they actually use them in those, they actually use a ring of platinum in those lighters. You know those jet lighters? You press them and you get a blue flame. Those jet lighters have a little ring of platinum that helps catalyze the reaction in the burning of the butane. So that, you know, you can light it in a fire and the thing won't go up because it burns the the butane very quickly. So the butane, the platinum will get white hot. But once it cools down, it still has a silvery look to it. It won't react with the oxygen in the air. You ever notice a motorcycle muffler? If you look at a motorcycle muffler, you see discoloration when the metal is closer to the exhaust where the engine, where the hot gases come out of the engine. Why does that happen? Why do you get a dark part and then you get all these rainbow colors on the muffler of a motorcycle? It's because the hot gases coming out of the motorcycle are so hot that they heat up the outside of the pipe to the point where it reacts with the oxygen in the air. So even though the pipe is chromed, it ends up being discolored after a while. And that's because it's very hard to make a metal that won't react with something at high temperatures. I suppose you could make a muffler pipe out of platinum, and it would be nice and silvery even after it cools down. But your motorcycle would be a lot more expensive with a platinum pipe. All right, so this is the activity series. And the activity series basically lists atoms from the highest, very often the highest oxidation potential and the most reactivity. You'll notice lithium is right at the top, and lithium happens to have the highest voltage. If you look at on that list of oxidation potentials, lithium has the highest one, 3 volts. And that's why we use lithium to make batteries, because it's the lightest metal in the universe, and it's also the one with the highest voltage. Just a little reminder from God that he's thinking about us, because he could have made uranium have the highest oxidation potential, and all our batteries would be twice as heavy now, because uranium is almost twice the density of lead. But instead, he was nice. He made lithium be the one with the highest oxidation potential. So let me give you an example of how this would work. Suppose you took an iron nail, which is solid iron, and you mixed it in a solution of copper sulfate, or copper sulfate would work. If you do that within seconds, you can take a copper nail, an iron nail, and stir a solution of copper sulfate, which is blue in color, and within a few seconds, the nail will be coated with a layer of copper. The copper will be solid on the surface of the nail, and some of the iron will actually dissolve off the nail, and it'll form aqueous ferric ions, or ferrous ions. Let's say ferrous, it'll be easier to do the formula. So what happens is the iron and the copper actually switch places. Why does that happen? Because iron here, copper is over there. So iron will give its electrons to copper. If it's higher up on the list, it gives its electrons to the ones that are lower on the list. So the iron will force the copper to take the electrons. The copper will become reduced, and the iron will become oxidized, and it will go into solution. That's why car manufacturers never use copper rivets. You never mix metals when you want things not to rust. If you make a fence and they have copper arsenate sprayed on the wood to prevent it from rotting, you can't use regular screws because their screws rust when they get exposed to the copper in the fence. So you need special deck screws that are coated so they don't actually touch the metal in the wood preservative. So there are all kinds of things like that. Car manufacturers discovered a long time ago that you either have to use plastic rivets to hold car panels, or you have to use rivets that are the same metal as the metal that the panel is made of, or they have to be made of a metal that doesn't react with the car panels. So there are all kinds of things like that. When they made the Statue of Liberty, they didn't know this. Or whoever made the Statue of Liberty was not a chemist. And the Statue of Liberty had an iron skeleton, but the outside, the cladding of the statue was made of copper. Well, iron and copper are not a good mix because this happens. So the places where the Statue of Liberty was connected to the skeleton just formed these huge deposits of whatever chemicals were produced from that reaction. And they soon discovered that they had to separate the statue from its skeleton to prevent that reaction from happening. So you can never, basically they made a giant battery. If you connect copper and iron directly, you will have a giant battery. And at that spot where the metals have contact, you'll have extreme corrosion of the iron, and the copper will be coating the iron. So they had to separate it by putting rubber grommets. So I don't know, I've never seen the inside of the Statue of Liberty, so I wouldn't be able to comment on it, but this is what I've read about. And chemically speaking, it makes sense. They use this process also, or they recognize this process when they make pipelines. If you make a pipeline out of iron and you bury it underground, one of the problems you have is that the pipeline will rust. So what do? They take a metal that is higher than iron on the activity series. Usually magnesium is a good choice. They take a big piece of magnesium and they connect it with a wire to the iron pipe. And they bury it with the pipe. And what happens is the magnesium will give electrons to the iron, preventing it from rusting, and then this piece will rust in its place. It'll corrode in its place. That's called the sacrificial anode. They do it on ships. They can even do it on cars. The sacrificial anode on your car is the muffler. It's the part that rusts the fastest. But it's easy to change the muffler, so it's no big deal. When you replace your car muffler with a stainless steel muffler, guess what happens instead?
So, if that's what happens with the copper and that come together, why do you think they just did that because they didn't know at the time, or something else?
Well, somebody knew it, but not the guy who made the statue. Kind of like what happened when they built the Brooklyn Bridge. There was a lack of intersection between knowledges of science. The people who built the Brooklyn Bridge, this is just another example, they used what are called caissons in French. It's a French word for basically a large case. So they took these big boxes, they turned them upside down and sunk them to the bottom of the river. And the workers would go inside the box from a hatch on the top, and they would climb down with a ladder, and then they would dig in the muck of the river inside the box. So they'd be underwater, but they'd pump compressed air and they'd push. So here's the river, here's the river bottom, and the workers would be in a box underground, underwater, and they would have a hatch going to the surface, I guess, which would be floating on a dock or something. So they'd climb down this hatch with a ladder, and then they'd work in the muck, digging, and then they would get rid of the mud somehow, I guess going through the hatch again. The workers would sometimes work 8-hour shifts in this pressurized box where they had high pressure air because the water wants to come in through the bottom. So to keep the water from coming in, they have to pump in high pressure air. Well, you're working an 8-hour shift in the pressure of maybe 3 times normal atmospheric pressure. Your body absorbs nitrogen. So when the workers would come out of the box to normal air pressure, they would get air bubbles in their system. Just like if you open a bottle of 7-Up or Sprite, when you open that bottle, what happens? All these bubbles appear in the bottle. The same thing will happen to your blood. If you're at the bottom of a river and the pressure is 4 times higher than normal air pressure, and you suddenly come to the surface, you get little bubbles appearing all over inside your body, which is deadly. If it happens in your brain, it'll kill you because it prevents the blood from flowing into the little blood vessels. So it's called the bends. You've heard of the bends? They used to call it caisson disease. Well, this was known by medical science, but it wasn't known by engineers. So there's a lack of intersection between the sciences. Knowledge that was contained by one group of scientists was not successfully passed on to another group of scientists, and so they suffered for it. Even the engineer, the main engineer who designed the Brooklyn Bridge, whose name I can't remember now, suffered brain damage because of the bends, because he used to go down to talk to the workers and encourage them, and then his wife had to take over the operation of the program, which turned into a disaster. To this day, it's kind of like a meme. You ever heard anybody saying, if you believe that, there's a bridge I want to sell you? You heard that expression? That's what that comes from, because there's so much dishonesty that went around that bridge because the main person in charge got sick that people were selling construction materials to the contractors at way inflated prices because the money was just flowing. So it attracted sort of piracy. Anyway, that's where we learned about the bends and what it can do to construction workers. Since then, we've learned that you have to decompress for a good long time to let the nitrogen out of your bloodstream before you come to the surface. Anyway, getting back onto the things you should memorize, this is for the activity series. So anytime you have a single displacement reaction, like we learned in grade 10, how do we know the reaction is going to happen? If the metal that is solid is higher up on the activity series than the metal that's already in the ionized form. So in this case, you can get a reaction. If you had it reversed, you'd get no reaction because copper is lower down on the activity series. It won't donate its electrons to iron. What else? You should know the trends in the periodic table. 4 trends I'd like you to know about are ionization energy, electronegativity, electron affinities, and atomic radii. Atomic radius, here the singular. So what is ionization energy? It's the amount of energy required to remove an electron from a gaseous atom. And they always measure it in terms of moles of atoms. So energy required to remove an electron from a gaseous atom. It's always done per mole, of course. And ionization energies are less for metals. Why? Because metals more easily give up their electrons. Ionization energies tend to be higher for nonmetals because nonmetals like to take electrons. So the trend for ionization energies, if you could draw yourself a little mini periodic table, increase from left to right and from bottom to top. The easiest metal to take an electron from would be something on this side of the table. The more metallic the element, the easier it is to take electrons away from it. So if you could find some francium on the Earth, it would have a very low ionization energy. If francium could be, if it was a stable element, it would make the ideal coating for an electric eye or for an infrared camera. As it is, we use cesium. Cesium is easily ionized, so they use it as a coating on lenses for infrared cameras, so you can detect people in the dark. Electronegativity is a measure of an atom's attraction to electrons within a bond. Electronegativity increases this way and this way. This one also increases this way. Pick it up tomorrow. And we'll finish off question 915 tomorrow, because that'll be the first thing we do after.